Yeah. Okay, welcome everyone to free session 4. I'm here with Gerardo, and tonight we're going to be talking a little bit about how to draw circuits, implementing basic breadboard circuits, um, and some software that you can use to design your circuits before you go ahead and implement them, just to streamline a little bit and make it easier. So let's go ahead and get started on the circuit design software. Circuit Lab, the first one, is free and it's online. It does require you an account that you sign up, and the kind of downfall of Circuit Lab, even though it's free, is that you only get a limited amount of designs before they basically log you out and ask you to pay the fee. I don't remember the fee, but most people just create multiple accounts with different emails if they're going about using Circuit Lab. That way they can basically create 5 designs, and then when they get locked out, go into their new email account and use it again to make more designs. Or you can use eDraw, which is also online. You can actually download eDraw for free, but it's very complicated, and it's kind of more similar to a PSpice, which is a little bit more complicated type of designing. It's not used for very basic circuits like breadboarding. The one that I like is this last one, Fritzing. I got it when it was free and they were requiring only donations, but right now it looks like they are requiring $9 to download. But this circuit, this picture of this circuit diagram that we have right here was made in Fritzing, and it's very user-friendly. And I like this breadboard view where you can see the actual images of the components you're working with, instead of like the circuit diagram component, which is a little bit easier to see. Okay, so getting into breadboarding, let's recall that the bus rows, these top rows, that's a bad arrow. These bus rows are connected horizontally, and all the other rows right here are connected vertically. And then there's a split in the middle of the breadboard, which allows for you to connect your components across the breadboard. And then another side note, that some breadboards do have a discontinuity right here. Oh, that one didn't pop up. Right there on the breadboard, on the top and the bottom. So just be mindful if you have that breadboard that you need to bridge the, put jumpers to bridge those bus rows together. So right here we have an LED push button circuit, a simple circuit that I was going to go ahead and build for you guys and demonstrate, but I made a common mistake that a lot of people make, and I left my battery plugged in, which eventually drained all the current out of the battery, and I didn't have any replacement batteries. So I'm just going to talk about the fritzing diagram that you see right here. So basically we have a 9-volt battery with the positive and negative terminals connected to the bus row. And then we have a push button right here, which is always connected. Let me see. So the long side right here is always connected, whether it's depressed or not. And so when you make any connections, you make it across the short side right here. As you can see, I have the resistor connected across. That way, when I depress the push button, that there's now a connection formed right here between those two columns of the 220 ohm resistor and the other leg of the push button. And then after that push button is pressed down, the current's going to flow through the resistor to the LED this way. And be mindful that when you connect your LEDs, they do have a polarity. So you can see I have the positive leg connected first, and then the anode is connected on the other side. That way the current flows through. Clear. And then the current then flows back through to the negative bus row, which then completes the circuit, and you're able to then use your circuit, and you can press down the push button and see the LED turn on. So that's basically it for that circuit. One note I wanted to make is if you're using fritzing and you build a circuit like this, fritzing does have a feature where you can just test your circuit and it'll test all the connection for you. And that's really helpful for 201. You can build your circuit quicker on here and make sure you have all your connections to your IC chips correct. Let's get rid of that before you go ahead and build it in real life. And it's a little bit harder to troubleshoot in real life because then you have to use test voltage across certain components and make sure they're connected. So here I have a LED dimmer circuit. I've demonstrated this one in the past, but it's basically the same setup. So I have the positive and negative terminals of the battery connected to the positive and negative bus rails on the top. And then since I made this circuit go all the way across the breadboard, what I then did was I used 2 jumper cables over here to connect the other 2 bus rows. And then I did this just for perspective, so you can kind of see it better on the way, because this potentiometer kind of gets in the way of all the connections there, so that's why I jumped it across. So then you can see I have the positive connected to this left terminal, left terminal on the potentiometer, and the left and right terminals are arbitrary. You can choose either one to be the positive or negative, but in this case I chose the left one to be positive. So the current then goes through this left terminal, and the center terminal is always ground, so it's then grounded, and the current then leaves through here, goes through the resistor, and then again goes through the positive leg of the resistor or the LED, and then leaves through the negative, the anode, and then back to the ground of the bus row, which then completes the full circuit back to the other side of the breadboard to using this cable right here. That's a bad, probably cannot circle them because they're so close. And then that completes the circuit right there. And we have one last one. This shows how the current is affected by resistors in series versus 2 resistors in parallel. So the first part of the diagram, we have 2 resistors in parallel right here. And what that does when you put 2 resistors in parallel is the equivalent resistance then becomes 1 over R plus 1 over R. So you can see if we were to have 2 220 ohm resistors, then the equivalent resistance then becomes 1. Sorry, I need to do the math. Yeah. 0.09. Let's do that to a fraction. It's not working. Okay, well, if you can see that, for simpler math's sake, if I do, oh God, 1 over 2 plus 1 over 2 then equals, this pen. One, sorry, there we go. So the equivalent resistance would be 1 if I had 2 2-ohm resistors. And then over here I have 2 resistors in series. So again, if I had 2 2-ohm resistors, it would be 2 plus 2, and this equals 4. So when you have resistors in series, the equivalent resistance is double, as long as these resistors are the same. So in essence, the resistors in series, the resistance adds together, and then when they're in parallel, you add 1 over the resistance. So that would result in this LED right here. There's less resistance for this LED, so the LED would be brighter. And then this LED right here would have more resistance, so you would see less current flow through, which means the LED would be dimmer. And that's it for these breadboarding diagrams. And Gerardo was kind enough to put together a live demonstration for an IC circuit diagram or IC circuit on his breadboard. So he's going to go ahead and demonstrate that real quickly. See,
all right, so
stop share, and I need to pin your. There we go.
I'm gonna share my screen first.
Okay, go ahead.
So yeah, so one important thing about integrated circuit chips is that one of the first things you want to do is because you're just going to see a bunch of pins on the chip, and then you're going to see some numbers on top of the chip. The numbers are going to indicate what kind of chip you have. So the chip that we're going to be working with today is a 74HCT00, which is basically just a NAND gates, 2-input NAND gate chip, and there should be 4 NAND gates within this chip. So what you want to do is just do a quick Google search up here, and you're going to get a bunch of results. But typically, just kind of the first one should suffice for the most part. And what you're going to see is something like this. And this is basically, I believe we talked about it last week. This is a data sheet for our specific chip. So like I said, today we're working with a NAND gate. And if we scroll through the document, we can see here that we're able to, it actually tells us what the gate is. And like I said, it's this one's a NAND gate. So it even gives us a truth table here. Inputs of high are low, inputs of low and high are a high, and inputs of low and what is this? I guess these meant zeros. They don't really matter, but the outputs here are high. If either one of the inputs are low, the output will be high. But the most important thing to know is the stuff here, which are the pins. So as we'll see later on, I'll show you directly on my breadboard in a little bit, but the pins go in a counterclockwise motion starting from the top left, goes down, goes to the next column, and then goes up. So it's important to know typically on the most bottom left and then the top right are going to be your ground and your power respectively. And another thing to note is this little notch here, and you're going to see that directly on the chip. So this is what I used when figuring out how to where to plug stuff in for this circuit. And so now we're just going to run through a demo of the circuit. So we want to pin the video now. All right, can you see everything?
Yeah, looks good.
All right, cool. So here we have our chip. As we stated before, there's a split down the middle in the breadboard. And this is really made kind of for the integrated circuit chips so that the pins here on the sides, the inputs and outputs or whatever they may be, are separated from one another. So starting from the top left here, it looks good on camera. You can see that there's a little notch right here. So like I said, you typically start on the top left and you make your way down here and up here. And I've already made a couple connections here. This one here being the bottom left pin going to ground, which is ground stated in the data sheet. And then we have the top right pin going to power here. And that's basically how you would start. All this other extra stuff is just for demonstration later on, but you would typically want to make sure you're connecting your ground and your power. If either one of these is missing, your integrated circuit will not work. Your IC chip will not work. So now we're going to get onto some demoing. So I believe the inputs, you would see this in your data sheet, but for this one I kind of have it memorized already. The top two right here on this specific chip on the left hand side are inputs, and then the third one will be our output. So if we make two connections here, these are going to act as our inputs. And now the thing is, where do we connect these two things? And to get highs and lows for your integrated circuit chips, when you kind of go into 201, they're basically zeros and ones. You're either connecting them here to ground, or to your positive, which is your power. And one really important thing to know is that you always want to bridge these parts right here. So if I were to do that right now, it's really just as simple as plugging in a wire from this positive part onto the other positive, and then plugging in the wire here from this, all right, from this negative part here, which is the ground, onto the other ground. So now everything here is connected, all these grounds and all these powers are connected. So the next thing would be to connect our output. So now for our output, how do we know what our output is? And the easiest way to do that is just to connect your output, which like I said was the third pin, and just connect it to something as simple as just an LED. So whenever our LED turns on, we would know that our output is a high. So now what we would do is use a power supply, or just something simple. Here I just have these 4 batteries, which just supply 5 volts to the circuit. So now the hot wire, the red one, should go into positive, and the ground, the black one, typically goes straight into the negative. So like I said, this is a NAND gate. Does it look good, Lakota?
Yeah, it's the color that the LED is kind of off, but you can tell it's on.
That looks better,
That's
right?
better, yeah.
Okay, so that's just to show that the LED is on. So hopefully you can still see me moving around these inputs. So like
Yeah.
I said, for a NAND gate, when you have 2 lows, both of these inputs here are connected to a ground. So that basically means your inputs are 0 and 0. And with a NAND gate, when you input 0 and 0, your output is a 1. So if we were to switch one of these to the positive, it still remains 0 because 0 and 1 in a NAND gate is still a high. And similarly, if we switch this back to 0 and this one to 1, our LED is still on. Now the LED should turn off when we connect to the positive, which it does.
Nice.
So if you do everything right, and that's like that's really important in breadboarding, is that if you do everything right, everything should function properly. So this is basically a simple NAND gate, but now kind of getting into a little bit more of the 201 kind of stuff. You can actually make an AND gate out of this NAND gate, and it's really as simple as taking this output here and inputting that output into another NAND gate. So essentially what that would be doing is inverting our output. But see, one thing that we're missing now is that we have nothing here connected to the LED. So one last connection would be from this new output into the LED once again. So now it's still not working because there's no power being supplied to the circuit. So once I plug this in, LED should remain off though. So now our inputs are 0, 0 for a regular AND gate. If your inputs are 0, 0, 0, 1, or 1, 0, your output should be low. And if we switch stuff around here, we're going to see that that's true. So that was 0, 0, 0, 1, 1, 0. And now if we both connect these to positive, it should be on, which it is. So this is kind of because NAND gates can be used universally, meaning you can use a NAND gate to create an AND gate, an inverter, an OR gate, and even a NOR gate. So just to keep running through a little bit more of the simulations now, if we disconnect power here and we make a couple more connections, we should be able to see an OR gate, if I remember this correctly. Should be something like this. Okay, so now looks a little complicated here, but essentially what we're doing is both of our inputs are going into two inputs of an AND gate, which will invert our inputs, and now those outputs go into another NAND gate, which in return should make the output function as an OR gate. And like I said before, if I did everything correctly, from my knowledge, this should work. So now we supply power once again to the circuit. And now our inputs are 0, 0. So as soon as we input 0, 1, this should turn on. And we see that that is the case, that is true. So for OR gates, your inputs 0, 0 would result in an output of high. And if we have inputs 0, 1, 1, 0, or 1, 1, no, sorry, if the input's 0, 0, you should have a low, which means your LED is off. But if you have an input of 1, 0, 0, 1, or 1, 1, then your output should be high, meaning the LED turns on. So let's change this input to a high, our LED is on. Now the other one to a high, our LED is on. And if they are both high, our LED should still remain on. And like I said, NAND gates are universal. So I believe one more configuration that we can kind of make here is using a NOR gate. So if we do something like this, or we connect this here, and this serves as two the same inputs, meaning we're inverting. Then we take this last output here. Now, if I did everything correctly and we supply power to the circuit, now for NOR gates, our inputs are as follow. 0, 0 would result in an output of 1. I believe 0, 1 should be 0. 1, 1, 1, 0 should also be 0, and then 1, 1 should be 0. So these are both high, the output is 0. It's high, low, the output is 0. And a different kind of high, low, it outputs still 0. So now when I move this white wire down to ground, this LED should turn on if I did everything right. And that is the case there. So
Nice.
yeah, so this is kind of how you would be using an integrated circuit chip. It really just comes down to practice with just integrated circuit chips, or really just breadboarding in general to have it down. There's a lot of stuff that can go wrong, not to intimidate you, but there's just sometimes there's just a lot of stuff, and really just have to go into your breadboard and debug and just kind of go through every little bit of it, and without fail, you should result in a functioning circuit, one that you want to function correctly. So that's basically it for the demo, the live demo at least.
Yeah, so like Gerardo said, there's a lot that goes into breadboarding, a lot that can go wrong, and it is a very tedious process, but you know, nothing that's good comes easy. And I can vouch that when you complete a successful circuit, especially when using IC chips and 201, is very rewarding. So yeah, not to intimidate you, we do encourage, if you go to instructables.com, there's lots of circuits you can see on there, using 555 timers, and capacitors, and lots of different circuits using IC chips that you guys can check out for yourself. They have step-by-step instructions, kind of just how Gerardo went through his. That's a really good way to get more practice and exposure to an experience with breadboarding. So that's basically it for tonight. Thank you for watching, and we hope to see you next week on week 5.